I'm Tomas. I'm one of the co-founders, CEO of Not Diamond, and we're a multi-model infrastructure platform. And today I want to talk to you about model routing, what it is, and also how you should think about this if you want to build your own router. I also just got the low battery sign, so I don't know if there's a charger I can add in here. So sorry about that. Okay, so just really quickly, this is us. We're a bunch of researchers, serial founders, machine learning engineers, backed by some great folks. And I'm gonna just start by defining what model routing is. So as Sean was saying, there's a ton of models out there, and broadly, you can think of routing as choosing the right model, but there's a couple different interpretations of this, right? So there's model gateways. So, for example, like if you're familiar with I'm blanking on their name, OpenRouter, for example, or LightLM, or a bunch of these other gateways which allow you to deterministically choose which model to use. There's also fallback rerouting. So if one model goes down, rerouting to another model or another instance of the same model on a different provider. And then there's dynamic routing, which is what I'm going to focus on today. And dynamic routing is sending each input to the best suited LLM. So this is an example. Oh, thank you so much. I think I'm on this side. Oh, no. Well, I'll probably survive. I probably have enough juice if we don't make it. But basically here you can see an example of if we ask what is a database migration, that's something that can be handled by a very small model, Gemini Flash, for example. If you want to write a database migration script, you're probably going to need a more powerful model. And one caveat I'll make is that we want to do this predictively, right? So there's a version of this where you just send it to every model and then you compare all the results and use another model to maybe pick the best one. That's very expensive and slow. So we're going to rule that out and say we want to predict before we call the model which model we're going to use. And just quickly before we get into how to do this, why you should care. We've talked to hundreds of teams that have been trying to build routers in-house. I think there was just a talk like 15 minutes ago in the Gold Room about someone building this out, and it's really hard. And but the benefit is that if you can effectively route your requests to the right model at the right time, you improve accuracy over any one individual model. You can lower your costs by using smaller models. When doing so, doesn't degrade quality. And you can also dramatically accelerate your engineering cycle. So there's a few strategies here. So the first is task level routing, heuristic routing, complexity classifiers, and ranked recommendation systems. So I'll go through each of these. My battery is up here. I'll remove that so it's not blocking the text. So the most common type of routing is just task level routing. So you maybe have one button, like a summarize button, you send that to one model, and you have a different button for writing, you send that to a different model. And the pros of this approach is that it's simple and transparent, but the cons is that it's not really giving you any of the real benefits of routing, maybe at a very coarse grained level. But this is, still qualifies as some kind of maybe the most general type of routing. But the next level is heuristic routing. And this is, I think, where a lot of people focus. So here we're basically defining manually conditional statements. And so one way of doing this is there's techniques around semantic routing where we maybe put together a few examples of hey, these are statements about politics. If it's about politics, send it to this model. And these are statements about data engineering. And if it's about data engineering, send it to that model. You can also use an LM as a router. Just give it instructions for which categories to send to which models. We've seen people use regex to do this. So the pro of this approach is that it's fast. It's easy to swap in and out models. A new coding model comes out, we'll send coding coding requests to that model. But the cons are that it's very brittle. We see teams start to develop these spider webs of if-else conditions, and also model capabilities don't really map onto our human heuristics, because even within Python coding, you might have some inputs that one model does better at and others that another one does. And when a new version of the same model comes out, it's weirdly worse on this category. And now you have to re-architect. It becomes incredibly high maintenance, and it doesn't scale. It's hard to onboard new models or swap them out. It becomes super linear. The effort grows super linearly with the number of models that you're managing. The next pattern is training a complexity classifier. So basically here, this is useful if you want to route between a strong model and a weak model. And this is especially helpful either if you're very, very early, and so you are maybe constrained on resources, or you're scaling to significant scale where it just doesn't make sense to send, potentially 80% of your queries could go to a cheaper model, but you need the bigger model for the more challenging queries. And so here we basically train a complexity classifier by evaluating how do either of these models do on our data set, and then we can tune what the threshold is. Like, okay, beneath this level of complexity, we're going to send it to the weaker model, and then above that, we're going to send it to the more powerful model. And so the pro here is that it's data driven, right? And I actually think I appreciate the last talk, because it's very, very, very hard to develop an AI if you don't have some kind of data about which models perform better or worse. And so I do think it's really important to move towards more data-driven routing solutions. And you can also drive significant cost savings. In some cases, we see 90% cost savings using these methods. But the cost is that it usually comes at some degradation in quality. You're never going to get equal to the better model or even better than the better model at some cost. So it basically lets you kind of flexibly adjust, depending on where you put that threshold between the quality of the powerful model and the quality of the weaker model. And the other downside of a complexity classifier is that it's frozen, so it doesn't scale. If you want to change that threshold, maybe you've validated in your evaluation stage, but then in production, it's not working the way you want. You have to retrain from scratch. If you want to have a different model, you have to retrain from scratch. And it breaks down the more models that you try to load in here. So this is really good for pairwise routing between two models, but it doesn't scale very, very well beyond that. And so the approach that we've taken is thinking of this as a recommendation problem. And so basically what we want to do is take, for a given input, we want to recommend the best model, or rather recommend a ranking of models for that input. And this is, I think, a nice, so the con here down you can see is that it really does require proper evaluation pipelines. But the benefits are that it allows you to scale very easily across n number of models. I mean, recommendation systems have been around for a few decades, can easily scale to millions of candidates. You can think Google is essentially a router from web search queries to websites. Netflix is a router from users to movies. And it also allows us to tune our cost and latency trade-offs flexibly without retraining on the fly. So basically, once we learn these rankings and these scores, we can use Pareto optimization to adjust our rankings. And it's very easy to onboard and offboard models because you can easily basically learn these mappings independently, or these ranking scores independently. So I'll show you what this actually looks like. But this is generally, I don't think there's a right or wrong answer, but I would describe these on a gradient of sophistication. And this is, I think, for teams that are moving towards, if you have like one AI application or two, you can kind of brute force it. But as you start to scale to like 5, 10, 20, some of our customers have hundreds of AI applications in production, it becomes basically impossible to try to do this all manually. So let me show you a really quick demo. I see the 5 minutes. Let me make my screen a little bigger. So I'm going to run through this really quick. Actually, maybe in the interest of time, I'm going to skip ahead to the end a little bit. The first part of this is basically we're just taking a RAG data set and we're going to generate responses from different models, in this case, 4o, 4o Mini, Sonnet, and Haiku. We're only taking 200 samples, so this technique does not need a lot of data. And we'll generate responses from the LMs. You can see this is boilerplate for generating the responses, but these are examples of what the inputs are. We have a question, the context we've retrieved, the response from the model, and this data set also provides the ground truth answer. We'll then evaluate these responses. We have a evaluation metric for hallucination over RAG data sets, but you can use any evaluation metric you want. And then we're going to train a router using this data. So we're just splitting it into train and test with an 80-20 split. And then we're passing into this trainer.fit method on the training data. We're passing in our inputs, the prompts that we've sent to these models, the responses from these models, and the scores that we've evaluated or assigned to each of those responses. And then we can evaluate this. So on the eval split, and this takes about 3 minutes. I'll just it might be a question in your minds. This is not an LLM, but it is a more traditional machine learning technique. So we are using machine learning to do this, but we're not using a language model. And so we're taking this trained router, and now we can evaluate this. And so on the test split, you can see this is the input. This is how each model is responding. It's GPT-4o, its score, etc. And this is the model that Not Diamond, our router, is recommending. In this case, it's recommending Sonnet, which scored 100%. On the second query, it's recommending let me get this scroll better. Our router is recommending GPT-4o. So it's learned to predict that we should use 4o on this input. And if you look over here, for some reason, Sonnet is scoring a 50% on this input. Now, to the human eye, it's basically impossible to tell why Sonnet would struggle with this question about hardwood flooring and not with this first question about public schools. But our router has correctly learned to predict that we should use 4o here. So at the bottom, we can see that the best average model here is GPT-4o. It's scoring 90% on this data set. And Not Diamond is scoring 93.5%. So just by picking the right model for each input, we've increased our, this score is the inverse of the hallucination rate. So we've essentially cut our hallucination rate by 1/3. And in addition, you can see this is the distribution. 1/4 of these queries are being sent to Haiku. So we've not only outperformed the best model, we've done so at 25% lower cost. At this stage, at the training step, we just maximize quality, but this is the dashboard view of what we just trained. And what's nice is that, I mentioned this before, we can now use Pareto optimization to flexibly adjust our cost savings, right? So maybe we want equal to GPT-4o quality at half the cost, or we want Sonnet quality at 1/4 of the cost. At the extreme, this sends everything to GPT-4o Mini. But basically, we can kind of flexibly adjust this. And maybe we deploy it and we're like, hey, we need higher quality, or we can get higher cost savings. We can do this without having to retrain our router. The other piece here I'll just touch on is that we can then, one of the great benefits of a recommendation system is that it's very amenable to continuous learning, right? So here we have the ability to set a sampling rate where every 1% of queries, we'll send it to all 4 of our candidate models and check, did the router actually make the right prediction or not? And we can use that to continuously improve the router performance over time. So I think I'm probably running low on time. So I'll just come back here. This is how we've built this, but yeah, I'll also just leave you with this kind of long range why, which is that right now, if you send 1 million queries to GPT-4o, it's always going to be the same model. But if you send 1 million queries through a routing system that can continuously improve, it's going to improve the quality and the accuracy of your AI workflows while lowering your costs over time. And that's, I think, a huge missing piece in the way companies are building AI. Thank you. I'll wrap up. Where you can effectively drive a data-driven flywheel on your own data without having to continuously retrain a foundation model from scratch. So I have here this first big QR code. I've put together a list of a bunch of model routing tools, including our own, but we also have an open source router that you can try, and also a bunch of papers. So if you're interested in this space, you can check that out. I also have my LinkedIn and Twitter. So if you want to connect with me, feel free. But yeah, I think I'll leave it there. Thanks so much.